This is somebody else's talk. This is my Carmelo's talk. Last, yeah, that one.
Okay, we are ready to begin again. The after coffee session is going to be then turned off by Sachin Vaidya, who is going to tell us about chaotic dynamics in the SU2 gauge model.
Thank you very much. And like everyone else, I want to thank the organizers for organizing an excellent meeting in an excellent location. Today, I want to tell you about chaotic dynamics in the SU2 gauge matrix model. And in particular, I want to show you that in this model is, in particular, what I want to tell you is that this model shows classical ergodicity breaking. So of course, when I say classical chaotic dynamics, I'm going to look at classical dynamics. And towards the end, I will try to make a connection between ergodicity breaking that we see in the classical model and quantum phases that you see in the quantum version of the SU2 matrix model. Okay, so this is joint work with my PhD student Chaitanya Bhatt and a summer student Vijay Nenmali, who is now on his way to Cambridge for his postgraduate work. Okay. This is how it's going to unfold. I'm going to introduce the matrix model for you and write down the matrix model in what are called singular value coordinates. So in other words, coordinates that correspond to doing the singular value decomposition. And I'll point out that for the SU2 matrix model, there is a tetrahedral symmetry that is not apparent until you go to these singular value coordinates. Then I will show you that this matrix model actually is the three-dimensional generalization of the well-known Henon-Heil system. Henon-Heil system is well-known in the two-dimensional Henon-Heil system is well-known and well-studied, and people who know about it also know that it has most interesting regular and chaotic behavior. So the fact that the SU2 matrix model in a particular corner is exactly the Henon-Heil system should be a clue that there should be interesting chaotic dynamics. So the way that we are going to go about developing this is to look at orbits of classical orbits of this model and show that they can be and argue that they can be classified according to this emergent or the new tetrahedral symmetry. And we are going to look at perturbations of these classical orbits, periodic orbits, and look at what happens when you perturb these orbits. If the perturbation is too large, eventually these orbits are no longer closed. They break and they become chaotic. So hopefully I'll have time to show you all these things. But the part that I found most interesting is that there is a set of orbits here which hang around only in one corner of the phase space. They do not explore the entire phase space, however high their energy. And this is a sign, classically at least, is a sign of ergodicity breaking. And I will also try to connect this particular phenomenon of ergodicity breaking to phases that come about because of selection sectors. Okay. So the matrix model is very easy to describe. It's made up of, these building blocks. You take 3 2x2 Hermitian matrices, or equivalently, you take a single 3x3 matrix with real entries. That's it. This is your configuration. These are your configuration variables, if you like. There's a little bit more. There's a little bit of a twist to the story because this this matrix M is acted upon by rotations from the left, like I've shown you. M goes to Rm, and there's also a gauge symmetry which corresponds to M going to MS transpose, where S because I'm looking at the SU2 matrix model, S belongs to the adjoint SU2, which of course is nothing but SO3. The gauge group here is add SU2 or SO3, and it's finite dimensional. What is the configuration space, which is that you look at all matrices and quotient out the gauge transformations, is the space of 3 by 3 real matrices quotiented by SO3. Now, it's already at this level, you can see that interesting things start, because if you look at the topology of this configuration space, this was worked out many decades ago by Narasimhan and Ramadas, and they showed that it has a quite unexpected and non-trivial topology. So it has you start off with an S5, take out an RP2 from the middle, from near this, take out an RP2, and then there is an R. So you're left with a 6-dimensional space, as you would expect, because these are 3 by 3 matrices and you're quotiented by a 3-dimensional group. This is a 6-dimensional space, but quite non-trivial topology. And I want to emphasize this part, that the topology is non-trivial, because this matrix model that I will write down is a popular, which instead of SU2, you can write it for SU3, SU4, SUN. It's a very popular model. So I think people talked about this model yesterday, today also, there were some people. But there is no reference whatsoever that people don't seem to care about what the topology is. And the topology plays an important role, because unless you pay due attention to the topology, you will miss many interesting things, or worse, you will find wrong things. And okay, so I won't have much more to say about topology, about the non-trivial topology. But to come back to the matrix model, again, these mathematicians, Narasimhan and Ramdas, they showed that you can write on something like a curvature, which is just, it has a linear term in it, which goes like M, and a commutator term. And this model, which the Lagrangian of which I will show you in the next slide, is actually a natural reduction of the full SU2 Yang-Mills theory on S3 cross R to the matrix model. So this is what it is. Although this is a very telegraphic construction of the matrix model, it has a nice rigorous derivation as the zero mode of the full Yang-Mills theory on S3 cross R. Okay. Now that was, I told you what the configuration space was. I told you how to write down the curvature. So, but in order to do dynamics, we need a gauge invariant Lagrangian. So what is that? For that, I'm going to need something which I will call an electric field, and that is the covariant derivative of the matrix M, and a magnetic field M, which is just the F that I had written down in the previous slide with the epsilon. The electric field is, as we expect, the time derivative of M. M is essentially the gauge field. So it's a time derivative of M and the commutator of M0 with Mi. And we can write down a formula for the magnetic field also, B. I should say chromoelectric and chromomagnetic fields. M0 is a parallel transporter in the time direction. And we are working in real time. We're going to work with time going from -infinity to infinity. So I can always choose a gauge in which M0 is 0. So here's my matrix model Lagrangian. It is what we expect from, it is exactly the Lagrangian that we would write down for Yang-Mills, E squared minus B squared. So, but because this is because M is a finite dimensional matrix, I have only finite number of degrees of freedom. I can think of this as a finite dimensional dynamical system. So the first term EI trace is just a covariant derivative of M squared, and the second term BI traced can be thought of as a potential for the matrices Mi. And many years ago, with Amilcar Queiroz Bal and I looked at this model, and we were interested in the entropic properties of this model. So I don't want to go into that discussion today, but that is why that is what started our interest in this model. Okay. Now, if you look at the formula for the potential, it's the square of B, and B has a linear and a quadratic term. So B squared has quadratic, cubic, and quartic terms. So V has up to quartic terms, and our matrix model is therefore, if you like, nothing but a multi-dimensional quartic oscillator. That's what it is. Now, in order to go further, we need to work with nice coordinates. So the coordinates that I'm going to use involve singular value decomposition, which is available for me very conveniently in this setup, because my M is a 3x3 real matrix. So I can do singular value decomposition. It's going to be a little bit different from the way we normally learn about singular value decomposition in our undergraduate mathematics class. What we learn is that R and S are both orthogonal matrices, but I want to interpret S as a gauge transformation. So S, I would like S to be an SO3 matrix. So R is going to be an O3 matrix, and A is a diagonal matrix with real entries. So the entries of A, A1, A2, A3 take values all the way from -infinity to infinity. So this is a small difference compared to what usual singular value decomposition consists of. And this was first studied by Ivai in the context of pseudo-rigid bodies pseudo-rigid bodies, but the kind of pseudo-rigid bodies he looked at was a body with 4 particles. And this is this is the investigation that he did, and found that the singular value coordinates are most convenient for understanding this pseudo-rigid body. So like I said, S corresponds to gauge transformations, and the R, which is an O3 matrix, corresponds to physical rotations and also parity. Okay. Now, what we can do in order to simplify that Lagrangian is to define R inverse R dot. This is just the angular velocity. Well, this is a matrix, so it has 3. It has 3 independent real numbers sitting inside, because this is an antisymmetric matrix, and that's the angular velocity, angular velocity of corresponding to physical rotations, and S inverse S dot is the angular velocity corresponding to gauge rotations. So if we do that, we can simplify the Lagrangian to look like this. So there is an A dot squared term, there is a term corresponding to omega squared, lambda squared, and then there is a term involving A's and omegas and lambdas. And of course, there's a potential. Okay. So it's very easy to compute the Hamiltonian from here. But because this is a gauge theory, I would like to impose a Gauss Law Constraint. And in this case, the imposition of the Gauss Law Constraint translates to saying that there is no rotation whatsoever in the gauge direction. So I set all gauge velocities to 0. And today, what I'm going to focus on is I'm going to look at the gauge invariant sector, namely the sector with lambda equal to 0. And I'm also going to look at the spin 0 sector. So I'm going to look at no rotations, no physical rotations as well, configurations that are not rotating, and of course, configurations that are gauge invariant. Okay. The potential term that's here, V, if you look, this is what it opens up. This is just nothing but B squared. And like I said, there is a quadratic, cubic, and a quartic term. And if you plug in the singular value, if you plug in the singular value ansatz, then it depends only on A's. The R and the S dependence drops off. And this is what it looks like: quadratic, cubic, and quartic pieces. What is nice is that in these coordinates, the A's, when you write out in terms of A1, A2, A3, this potential has a tetrahedral symmetry in the variables A1, A2, A3. And the full symmetry of curve, the Hamiltonian, when you include the kinetic energy term as well, is that there is a tetrahedral symmetry and time reversal symmetry. So the tetrahedral group, if you remember, is the group, finite group corresponding to the symmetries of the tetrahedron. If you include parity, then well, that group is order 12. If you include parity, it's a group of order 24. If you include time reversal, it is a group of order 48. Okay, and so this is a picture to show you what this tetrahedral symmetry looks like. So what I'm plotting are constant energy surfaces or constant V surfaces. So for very small energies, you can see that there is this tetrahedral structure. And for very small energies, the constant energy surface is broken up into 5 parts. There's a central blob and 5 minor blobs, 4 minor blobs, a total of 5 blobs. As you increase the energy, the central blob grows and these side lobes, they also grow till you come to a critical energy, 3/32 or whatever it is in decimal notation. And that's when the central lobe and the side lobes touch each other. And then if you increase the energy further, then this becomes some tetrahedral shaped blob. But if you increase the energy a lot, then there is an approximate emergent octahedral symmetry. So this is what the symmetries of these are the symmetries of our Lagrangian or our Hamiltonian in the singular value coordinates. The tetrahedral symmetry remains exact, and the octahedral symmetry is there is a very close connection between the tetrahedral group and the octahedral group, and there is a precise sense in which one tetrahedral group sits inside the octahedral group. So for large energies, the effect of the octahedral group dominates. Although if I look at it closely, the tetrahedral symmetry is still present and exact.
I expected flat directions here.
There are, so
I should see, but even for zero energy.
There are no flat directions because the potential is quartic, and so it's confining.
Oh, you have added that mass term. Okay.
I don't want to use the word mass term, but I think in another avatar, the terms that I have an interpretation as mass term. Either in IKTT or BFSS, BMN, there is an interpretation as mass. I am looking at a pure Yang-Mills theory on S3 cross R, and there is no mass for me. Tetrahedral group is acting on A1, A2, on the set A1, A2, A3. It is a 3-dimensional tetrahedral group. Yes. Which one? Yes. What do you mean by it is in 4 dimensions? Yes, tetrahedron has 4 corners, and it is all the SO3 transformations that leave the tetrahedron invariant. It's a 3-dimensional representation of TD. Yes. Yeah. Yeah, it doesn't act on real space. It acts on these A1, A2, A3 coordinates. Yeah. Okay. Okay. So let me also tell you something about the potential. It has, if you try to look at its extrema, then they occur at when all 3 A's are equal, and in particular when that equal value is 0, half, or 1. Now you can also compute the Hessian, and it's positive when the A's are 0 or when all the A's are 1. Positive definite, and these are the minima. M equal to half is a saddle point. So there are 2 minima. It's a potential in 3 coordinates. So there are 2, but roughly speaking, there are 2 minima. They are connected by a saddle point. Okay. There are other minima and saddle point that can be obtained just from these guys by doing the action of the tetrahedral group. Okay. So let's look at the color zero, spin zero sector. So that's very simple to write down. I just kill the terms that have omegas and lambdas in them, either before or after the Legendre transformation, preferably after the Legendre transformation. But this is what the Hamiltonian looks like. There is a P1 squared, P1 squared, P2 squared, P3 squared, the kinetic energy term. And then there's a quadratic, cubic, quartic. But this particular form of the Hamiltonian was recognized by these people, Eustathio and Sadowski, about almost 20 years ago, as the three-dimensional version of Henon-Hiles. And that is already very interesting, because what it means is that in this sector, spin zero, color zero sector, the SU2 matrix model is exactly the three-dimensional Henon-Hiles. And the two-dimensional Henon-Hiles is a exciting model for cosmologists, for people who study galaxies, people who study chaos. And I hope that this reason the connection with the SU2 matrix model will give a similar excitement to the three-dimensional Henon-Hiles model. Okay. This model is, of course, nonlinear. So what do I mean by nonlinear? There are these cubic and quartic terms. And as I showed you, this constant energy surface that I drew earlier, it has 5 pieces if the energy is less than a critical value. And then the constant energy surface is a connected piece for energy greater than this critical value. This critical value, 3/32, is actually the saddle point when all the A's are equal to half. So what I'm going to do is I'm going to rescale the A's and rescale the P's in the opposite way in order to preserve the symplectic structure, to write down the Hamiltonian as a three-dimensional isotropic oscillator plus a cubic term plus a quartic term. The cubic term has an epsilon sitting next to it. The quartic term has epsilon squared sitting next to it. And epsilon, if you like, it's obvious from the way that this Hamiltonian looks, is a measure of nonlinearity. When epsilon is 0, we have the three-dimensional isotropic oscillator. And the three-dimensional isotropic oscillator, it has only closed orbits. When you turn on the epsilon, then there is a old, but also, in my opinion, quite deep theorem coming from Weinstein, who argued that this system has what are called non-linear normal modes, and they continue to exist for sufficiently small epsilon. This is apparently a well-known theorem. I found out about it only a few months ago. Okay. And these nonlinear normal modes are characterized by the stabilizer of this 48-dimensional group, 48 element group. And long time ago, these gentlemen, Montaldi, Roberts, and Stewart, sat down and wrote out the classifications according to classification of the orbits according to the conjugacy class of the stabilizers. And they were also able to write down the number of orbits that you get corresponding to each of these. So, for example, what is called A4 has 3 orbits, A3 has 4 orbits, etc., etc. And I have here a picture of some of the orbits. So I'm sorry that there is supposed to be a tetrahedral structure here. I hope you can see it. Similarly, there is a tetrahedral structure here. So the A2 and the A3 are essentially straight line orbits. So A3 and A4 are straight line orbits. A2, although it looks like a straight line orbit, it is actually, when you look at it closely, it's actually a curved orbit. And B2, B3 and B4 are closed orbits. There are also other non-critical closed orbits, which I have drawn a sample one for you. Okay, so these are the various kinds of orbits that you have that come from the classification of the critical points from under the tetrahedral group. What we are going to do is we are going to study the perturbations about each type of orbit. And what will happen is that as you increase the size of the perturbation, as you increase epsilon, the orbits will destabilize. They will no longer remain closed. And typically what happens is that the orbits destabilize by becoming weakly ergodic. That is, if we calculate the Liponent exponent contains to be 0. Weakly, I will explain the weakly meaning of the phrase weakly ergodic maybe at the end. It's not necessary for me to say that just now. And then they become ergodic, which is when the Liponent exponent is actually positive and non-zero. So this, of course, happens for all the orbits. All the orbits, roughly speaking, destabilize in this pattern. But the orbits A3, A4, and A3, they destabilize in a most interesting manner. So this is what I'm going to tell you in the remaining time that I have. Okay. And the idea of the way the dynamical systems people, they study the destabilization of these orbits is through a technology called the monotony matrix. And what they do is they start off with a periodic orbit. It has some period t, and they look at a perturbation, small perturbation around this periodic orbit. And then look at the equation of more equations satisfied by this x. So this x of the periodic orbit, by the periodic orbit x, I mean a column vector a1, a2, a3, p1, p2, p3. Similarly, the little x is a column vector delta a1, delta a2, delta a3, delta p1, delta p2, delta p3. So I've just used a single label. But then if you look at the equation obeyed by the perturbation, then it's x dot equal to some function, actually a matrix that depends on the original periodic orbit times x. We can think of this equation equivalently as a time evolution matrix that takes the perturbation at initial time to a perturbation to the value of the perturbation at some later time. And this U is essentially the monotony matrix. And U has most interesting properties. For one thing, the simplest way to think about U is to recognize that it tells us what happens to the small perturbation as you sort of take it along your periodic orbit. The periodic orbit may be a loop, or it may be just going back and forth on a line. Okay. And eigenvalues of U, which in general they are complex, they carry information about the stability of the orbit. And in particular, so you can do this for any dynamical systems that don't come from Hamiltonian. But in particular, if you look at Hamiltonian systems, then the eigenvalues come in reciprocal pairs, and there's always at least 2 eigenvalues with value 1, and U is real, so they come in complex conjugate pairs. Okay. Now, the most important result, as far as we are concerned, and my guess is that it is the most important result in this business, is that a periodic orbit is unstable if and only if at least one of its eigenvalues lies outside the unit circle. So the eigenvalues are complex. You can compute its modulus, and if the modulus is greater than 1, then the periodic orbit is unstable. Okay. Now, for nonlinear systems, you can only find the orbits, periodic orbits, numerically. And the monotony matrix calculations are also therefore done numerically. For us, as I showed you a few slides ago, I showed you some pictures. The A3 and A4 orbits are straight line orbits. And we can compute these orbits as functions of time, and actually we can compute them analytically. So we can make much more progress with the monotony matrix calculations for this class of orbits. Okay, so let me quickly show you. Well, let me show you as fast as is reasonable what the stability properties of A4 are like. Okay. So these are my initial conditions. If I choose all the P's to be 0, 2 of the A's to be 0, and 1 of the A's to have a non-zero value A. Okay. And then I look at a fluctuation. I'm calling the fluctuations x1, x2, x3, p1, p2, p3 for the fluctuation of about the A's, and the I should have chosen a slightly different. Maybe I should have called them Q's. Sorry about that. The fluctuation equations are rather simple to write down. X1 dot is P1, P1 dot is minus X1. And x2 dot is p2, but p2 dot is x3, p3 dot is x2. So these equations are coupled equations, and if you, it's quite straightforward to decouple them. Just take the plus and minus, x1, x2 plus x3 and x2 minus plus these combinations, and the b minus is b plus and b minus. B minus, for instance, obeys the Whittaker-Hill equation. So Whittaker-Hill equation is this double dot is a derivative with respect to time, and eta is a constant related to my amplitude a, and then alpha and sorry, eta is the constant related to the amplitude. Alpha and beta are also written out in terms of my capital A. But one thing you recognize as soon as you look at this equation is that it is nothing but the Schrodinger equation for a particle in this particular periodic potential, right? That's what it is, and it has this energy eta. Maybe I missed a minus. Never mind. It has this energy eta. But we know a lot about particles moving in periodic potentials. You know that Schrodinger equation for a particle, it has the allowed energies come in bands and band gaps. So when the allowed energy, when the value of eta, which what I am calling allowed energy, to borrow from condensed matter terminology, when it is an allowed energy, then the corresponding wave function is a block wave function, which is some phase times a periodic function. And these correspond to stable perturbations. Whereas if I choose a value of eta outside the band, if I choose it in a band gap, then the solutions to the Whittaker-Hill equation are non-normalizable. And these correspond to unstable perturbations. So we can say more about this precisely because this is a rather simple and straightforward system. So if you, I forgot to say that B minus obeys a very similar equation. So the eigenvalues therefore come in pairs. There is a doubly degenerate, there is a eigenvalue 1, which is doubly degenerate, and there's lambda and mu coming from B minus, and lambda and mu coming from B plus. These are the eigenvalues of U. And because of the kinds of constraints I wrote down on eigenvalues earlier, you have to come in complex conjugate pairs. If lambda is an eigenvalue, 1 by lambda bar is an eigenvalue, and so on. For us, there are only two possibilities. This is the possibilities for lambda and mu are severely constrained. One is that the eigenvalues are real, but if they are real, then exactly one out of the two, lambda or mu, will be outside the unit circle. So that means the orbit is going to be unstable. And the other possibility is that they are imaginary, in which case the eigenvalues lie on the unit circle, and so they are stable or marginally stable. So this is more or less as far as you can get analytic. Now you have to go to the computer, and what we did is to look at the plot of trace M as a function of energy. We could have looked at the plot of gamma, but trace M is easier to plot. And numerically, we see what we saw is that all the orbits are unstable if the energy is less than 3½ And after 3½ there are quasi-periodic transitions between stability and instability. I say quasi-periodic because there is no set period. The size of the interval corresponding to stable motion and unstable motion, stable motion, unstable motion. This size keeps on changing, actually, in a manner that I will show in a rather interesting manner. So here are the pictures of trace M versus energy. So here is a picture for energy less, so very low energies. And the blue line is the value of trace M, and the red and the green mark +2 and -2. So for very low energies, the trace M is always greater than 2. And in fact, it is greater than 2 till you come till 3/2, till 1.5, at which point it's back to being equal to 2. And after which, here, for instance, there's a small region when it is between plus and -2. Then again, it is less than -2. Then again, here it's between plus and -2. so on and so forth. Oh, vertical axis is trace M. Trace M has to be between plus and minus 2 for the orbit to be stable, and it has to be outside this band for the orbit to be unstable. So this blue line corresponds to energies when the orbit is always unstable, and then there's a tiny region here where the orbit is stable. Again, here the orbit is stable, and then here I have plotted it for even larger energies, and you can see that there is a alternation of stability and instability, stability, instability, and this size, the size of the stable region keeps changing, keeps increasing. Okay. So let me also show you what happens to the A3 orbits. That was for A4 orbits, and for A3 orbits, again it's a straight line orbit, and this is the initial condition. All three A's are equal, all three P's are 0. Okay. You can solve the differential equation corresponding to the equation of motion, and now the orbit is not a sine or a cosine, but a more complicated periodic function. In particular, it's an elliptic function. You can compute the period exactly in terms of complete and incomplete elliptic functions of the first kind. I didn't want to write them down because I mean, there's no, you can't make, yeah, I didn't want to write it down, but I can tell you privately what they are. Again, you can look at perturbations, just like how I showed you. And if you look at the perturbations, you see that the perturbations again obey a Schrodinger equation for a periodic potential, except now the periodic potential is more complicated because the orbit is now an elliptic function instead of a cosine function. So again, because it's a periodic potential, there is a structure of bands and band gaps. And specifically, numerically, what we found is that if you're less than the critical energy, which is 3/32, trace M oscillates between plus and minus 2 with ever increasing frequency. I will show you a picture in a moment. And the peak spacings vary geometrically as we approach EC from below. So you start off from low energy and start approaching the critical value. The spacings vary geometrically. If you look at the other end, if you look at beyond the critical value, 3/32, then trace M again oscillates between plus or minus 2, but now the frequency is decreasing. I use the word frequency loosely. When I show you the picture, then the precise meaning of what I mean, what I'm saying will become clear. Okay. And in this case also, for E greater than EC, the peak spacings vary as a geometric series as we approach EC, but now you approach EC from above. Okay, so this is what it looks like. If I look at the y-axis is trace M, and the x-axis is energy. There is this oscillation. It starts off with above trace equal to plus 2, oscillates to below trace equal to minus 2, goes back up. But you can scale, you can zoom into this region, and when you zoom into this region, you see that this picture, which is a zoomed version of this picture, looks exactly the same. You can zoom in further, and this picture, which is I hope you can read the horizontal axis, the scale on the horizontal axis. But again, this picture is a zoomed version of this one, and this picture is a zoomed version of this one. You can make the same plot for the supercritical region, and again you will see that I can zoom in here in this region and the picture looks exactly like this one. I can zoom in on this region and the picture looks the same and the same. So those of us who remember about self-similar behavior will immediately recognize that this is a plot of a self-similar graph. Yes, I'm going to show you in the next slide. Okay, so the bands, band gaps have a self-similar structure as a function of energy, and we can compute the Feigenbaum constant for these. And it turns out that the simplest way to compute the Feigenbaum constant is to define this quantity, the how much the energy ratio differs from 1, and then you compute this ratio, compute this nu n by nu n plus 2, where the n labels a crossing at either 2 or -2, and then I have to take the n, the ratio of n and n plus 2, because if it crosses at +2, the next time it will be at -2, and then it'll have to cross only after that will it cross at +2. So this ratio nu n by nu n plus 2, for as you take n going to infinity, as you scale in, it tends to this value, e to the minus pi by square root of 2 by 5. I have never ever worked with this number before, and I don't know if I will ever find this number again in my research, but it is nice to find such numbers. But what the important thing and the interesting thing is that we get a different Feigenbaum constant on either side, for E less than EC and for E greater than EC. Okay. What about Liponov exponents? I told you that we need to look at Liponov exponents to discuss this chaos, strong or weak chaos. So here is a plot of the Liponov exponents. Again, these are only computed numerically. I think almost nobody computes Liponov exponents analytically, but this is for A4, and so these little horizontal lines at 0 correspond to stable motion. Liponov exponents are 0, and these ones are the unstable ones where you have non-trivial Liponov exponents, and with our experience we think, oh, this must fit to a log, and actually it does. You can see that it fits to a log. Okay. Numerically, this is, I've seen worse fits, you know. I mean, and people show worse fits and say, this is a fantastic fit. But okay. And these Liponov exponents, of course, they reflect the band structure. And this growth is logarithmic. You can easily calculate the exponent. You can do the same for the Liponov exponents for A3. Now, A3, if you remember, had this structure of bands getting compressed and compressed as you came to EC, and beyond EC they had bands that got stretched out. So numerically it's very hard to calculate Liponov exponent. That is, we didn't know how to do it. So we were able to find one band, and then the band stretches out. So as far as we can tell, stretched out, this is a band gap, and this is the band, and again the fit is logarithmic, so you can see a straight line. Okay, and here again the bands are wider. They're stretched by geometric progression. Now you can also ask, what are the Liponov exponents for a generic perturbation? And I really have to hurry up. This is what it looks like for a generic perturbation. Again, you can fit it to a log graph, and on the log graph it's a straight line. You can compute the straight line equation. But what I want to quickly talk about in the last 1.5 minutes is the connection between ergodicity and thermodynamics. For arbitrary initial conditions, we find that the trajectories are strongly chaotic in the sense that they have non-trivial Liponov exponents. For such trajectories, we can compute the time average of P1 squared and P2 squared and P3 squared, and we find that they are equal. So in that sense, equipartition holds and ergodic hypothesis holds, and we have numerical verification for that. Now, the Liponov exponents have an intimate relation to something called the Kolmogorov-Cyanide entropy, and many times people write this as equality, but if you go back and look at what Pessin wrote, he wrote that it is like an order of the sum of the Liponov exponents is like less than or of the order of the Kolmogorov-Cyanide entropy. Now, what you can do, this Russian mathematical physicist did a long time ago, is that for such ergodic chaotic systems, you can define a useful quantity called temperature. And what is remarkable is that the temperature and the Kolmogorov-Cyanide entropy obeys the known relationship between thermodynamic entropy and thermodynamic temperature. So again, we've checked this numerically, and this for us is, if you like, evidence that the system chaotic, when it is in the chaotic domain, is thermalizing in the sense of obeying the relationship between temperature and entropy. Okay. I will go through this fast. And you might ask, why did I spend so much time on A3 and A4? It turns out that A3 and A4, even when you look at a generic 6-dimensional perturbation, these trajectories do not explore the entire available phase space. They are confined to particular corners. And this, you can run it for a long Monte Carlo or numerical time. They remain stuck in these corners, and in this sense, they break ergodicity. They do not explore the entire phase space. The numerical evidence, an alternative one for this, is that in this corner, equipartition does not hold, which is again confirming that ergodicity is broken. And ergodicity breaking typically is thought of as corresponding to different phases. And I think in Yang-Mills theories, they are often referred to as glassy phase of QCD or glassy phase of Yang-Mills. So there are at least two corners, the A3 corner corresponding to A3 dynamics and the corner corresponding to A4 dynamics, where the dynamics doesn't break out of these corners. And a few years ago with my student, we looked at the quantum SU2 model coupled to quarks. And these system displaced quantum phases because of superselection sectors. And roughly speaking, what happens is that the quarks get trapped in special corners of the gauge field configuration space. So this is an impression of what the gauge field configuration space looks like. And the top tip, this one, is one such phase, and the side two tips, they're related to each other by parity, is another quantum phase. So the top tip actually turns out to be the classical image of the A4 trajectories, and the bottom one corresponds to A3 trajectories. So I just want to end by saying that by asking what is the quantum signature of classical chaos, and there is really no simple answer. All of us who are interested in this question are still looking for it. There are many answers. And to this list of many answers, now we have to add one more possibility, which is that classical ergodicity breaking can lead to quantum phases. So that was basically what I wanted to tell you about. This is my summary, and I want to end that. Thank you very much.
So this is not strictly a question about the model, but I was really surprised by some similarities. I'm doing machine learning, modeling, and this breaking of ergodicity, it is observed there, and people use thermodynamic model, which is very wrong, because of course, I mean, if you have so have you seen, some parallelism? No.
I started to look at this subject 6 months ago. So I know practically nothing about this subject. Practically nothing. Now I know epsilon. But I will look at the references for machine learning.
Yes,
please tell me.
Zecchina, Chaudhary, Soatto, these are the people doing the thermodynamic interpretation with ergodicity, but the ergodicity is breaking. So I don't know what they're doing.
Okay.
Yours seems a very nice model. That's all.
Thank you so much.
Okay. Do you have examples of quantum phases that you are sure not coming from classical breaking of ergodicity?
I know of quantum phases only in this context. Are you talking of in general? I don't know. I mean, maybe I suppose this is a general question, and maybe people who are the StatMech lattice condensed matter people may have an answer.
I would say that's not the usual way that people would think of that.
Okay.
So here's an example.
Yes.
You sorry, you mentioned color several times.
Color, yes, yes.
I have two questions. In which sense this is something like a two-color chromodynamics, and can you go to SU3, or the fact that you have these properties of SU2 which are peculiar to SU2 prevents you to go from
okay,
2 to 3?
Yeah. So it is. I call this color because you can show that. I mean, I didn't write down the Gauss law part corresponding to Lagrangian, but the A naught, M naught multiplies the gauge angular momentum generator. So if you, there is no M0 dot term. So even classically, the gauge angular momentum is a constraint. You impose that constraint by putting the gauge angular momentum to 0, which it turns out is the same as setting lambda equal to 0. So this is it is in this sense that this is a colored system.
But it's the dimensional reduction of Yang-Mills on R cross S3.
Yes, it is a dimensional reduction, so it remembers everything about Yang-Mills. And the other question that you asked is also very interesting and very important, because a lot of the things that I can do, for example, the singular value decomposition, is possible only because I am working with a 3x3 matrix, and it is possible for SU2. Nevertheless, I can write down the Lagrangian for SU3 or SUN. Writing down the equations for, then one will have to write down the equations of motion for gauge invariant observables, which are not difficult to construct, but it is more complicated. And here, of course, you see we had hindsight of expecting the quantum phase to occur at the tips, so we knew what to look for, and we saw the ergodicity breaking. For SU3, it's an open question, and it is an interesting question. It is an important. SU3 is the love of our
life. I have many other questions which
Yes.
I'll ask you privately, because
Yes.
we are running way behind.
Thank you.
Okay,
I'm so sorry.
that's okay. The next speaker. And yes, this is right, yeah. And the next speaker is Samuel Kovacik, and he's going to prepare us for a Greek salad with his fuzzy onion.
So thank you. Hello, everyone. This is a talk about the fuzzy onion, which hopefully won't make you cry. And recently, I have learned that I should start presentation with a disclaimer. So the fuzzy onion is an obvious name for something that is a rather obvious model. So it appeared multiple times during the history of our universe within last maybe 20 years. So this is another way how to formulate a fuzzy onion model, which for my selfish research interest is, I think, the most convenient one. And also this is a joint work with Uri Tekel, so if you are angry at me for a reason, also be angry at him as well. So, okay, so if there are already some models of the fuzzy onion space, of fuzzy spaces, quantum spaces in general, why to add another one? And basically, there are two good reasons why to develop a new model of quantum space or of anything, actually. The first one is of a mathematical interest. So we usually build theories that are nice and that they allow us to understand some aspect of maybe physics, maybe just mathematics. But also we are physicists, so we should at least to make sometimes a step towards some kind of experimental predictions, observational predictions, and so on. Until rather recently, when somebody asked me whether the physics I'm working on can be tested experimentally, my answer was, well, for that we need a particle accelerator of the size of the solar system. And then I laughed nervously and just carried on. But actually, this isn't true anymore. We probably cannot perform and Planck scale experiment, but we can make observations because Planck scale physics are relevant in the universe. So, for example, Planck scale physics changed the behavior of microscopic black holes. Last year at Corfu, I had a talk about a recoil effect on very small black holes due to Planck scale physics. And there is a huge area of research of dark matter being made of very small black holes, probably started by Nicolini, but I don't want to claim any priority on anything, so I will be very careful in trying to navigate through this minefield of topics people are very opinionated about. But something that actually, if I had to bet on something, what would be the observational effect of Planck scale physics we can hope to see during our lifetimes? That is the vacuum dispersion effect, which is basically the idea that if the space has some kind of quantum structure, different wavelengths of light travel at different velocities. So if you see a gamma ray burst traveling through the entire universe, some wavelengths can get ahead, and there is actually a proposal for a telescope to see this. But there is another thing which is called Gzk limit, which is basically some upper speed limit for cosmic rays, which is being surpassed by some particle. For example, the famous example, the oh my god particle, which had energy somewhere between LHC and Planck energy. So we have observed very energetic particles, and there are some conventional explanation why is it possible, but some of them are coming from the Planck scale physics. So this is a good review paper for this topic. And we have seen many interesting topics about basically something we can call matrix cosmology models. So we can also hope maybe not to see direct consequences of quantum space on, for example, the idea of inflation, but some sort of reformulation that is consistent with the current observation and probably missing some nasty properties. Okay, so a model, an example, very specific. There are many of them, but one of them was probably thought of by Peter Preschneider, and then co-developed by Veronika Galikova and myself during our PhD studies, which is basically a model of three-dimensional quantum space, which is defined by this non-commutative relation. Lambda is something you can think of the Planck scale or the scale defining the quantum structure of the space. And a possible construction of such space is using two sets of auxiliary bosonic operators acting on an auxiliary Fock space. So you can define non-commutative coordinates using polymatrices and do something with it. This model can be understood as a three-dimensional space consisting of fuzzy spheres of increasing radii. So you have a very small fuzzy sphere, larger, larger, larger. So the symmetry is broken down into a spherical symmetry and then a specific radial direction. And the radial direction is quantized in sort of a lattice way. So you have discrete distances from the origin and then some kind of fuzzy sphere structure on each of the fuzzy spheres. And there are other definitions. So for example, the one suited for quantum field theory using star product. But this is something we have been working on, which is very useful for quantum mechanics. So basically, we have the free Hamiltonian defined using the auxiliary bosonic operators. And with a free Hamiltonian, you just need to plug in some potential and study a quantum mechanical problem. So we spent some years on the hydrogen atom problem, which we are able to solve exactly. And this is the nice thing about this construction. It allows you to solve at least some nice problems exactly. So no perturbations, nothing like that. This is an exact result for the energy spectrum for a hydrogen atom in a quantum space. Obviously, we are not hoping to see some Planck scale corrections to chemistry, but this is the type of a model that is nice to understand what is going on. And funny thing is that, okay, so we obtain the energy spectrum. If you expand this, then those two ones cancel. And the first term is just the ordinary hydrogen atom energies, a constant over n squared, and then some Planck scale corrections. There is actually a second set of solutions with energies that are reflective in a way. So we have very small energies and then very large, on the order of Planck scale. And I mentioned this because some months ago there was a new paper by Nicolini about a way how to introduce quantum structure of space into path integral formulations, which uses this kind of small scale, large scale symmetry between distances. So maybe we can still learn something from this very simple model. Another very famous model of the quantum space is the fuzzy sphere. I can just gloss over some definitions, but a very similar definition as the previous one I showed you before. And fields on a fuzzy sphere can be described using something that you can call matrix harmonics, or matrix harmonics is probably the best word, which are basically finite dimensional representation of the SU2 algebra. So you have something that looks like this one. The first, I think the real history is the first it was guessed, and then showed that when you apply it on a, for example, function of a radial coordinate, it reproduces the ordinary Hamiltonian in the lambda goes to 0 limit. But then we understood it as you can construct this type of a space using starting with a 2 complex dimensional space, quantizing that as is equipped with a Poisson structure, and then just wrapping it together to form this one. And then you basically inherit this type of the Hamiltonian. So yes, but you can then ask me about some comments about this. So there might be some issues with this approach, and this is exactly what is being done here. So we have basically just applied it twice, and yes, 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 yes. So this is the Laplacian. These are the eigen matrices, as now finite dimensional elements are matrices. And with this, for example, you can do a field theory. So there are many studies and working with Denjo in Dublin, we studied the triple point of the scalar field theory on a fuzzy sphere, understanding what happens to this meeting point in the large N limit, trying to do some precision studies. And there are obviously many different studies of fuzzy sphere physics. I picked this one because just to understand my personal motivation behind all this. And we say that fields on a sphere, on a fuzzy sphere, can be described using matrices. So in a what way? In a what way does this Hermitian matrix correspond to a field on a sphere? So fields on a sphere you can expand using spherical harmonics, and this matrix can be expanded using the matrix harmonics, of which we have a finite number. So this expansion goes from L equals to 0 to N minus 1 and over possible M's. And this is it. And the thing you can do is you can take these expansion coefficients and then use spherical harmonics to produce a field on a sphere. And you will obtain a field that has some kind of minimal spatial resolution, in the sense that, for example, if you wanted to produce a delta function on a sphere using a 4x4 matrix, you cannot do it perfectly. You can just squeeze the field together, but there will be a small patch of non-zero area. Now, by increasing the matrix size, there are two ways of looking at it. The first is that you are improving the resolution. That means squeezing down the patch if you want to produce a delta function. The other way of looking at it is you are keeping the size of the quantum blocks or patches fixed, and you're increasing the matrix size. It's basically the same way of looking at it. So for example, you can take a 2x2 matrix and describe a small fuzzy sphere. Then you can increase the matrix size and have larger fuzzy sphere. And now you see the fuzzy onion coming together a little bit. So you have a very small fuzzy sphere, larger one, larger, and so on. So carry this out to infinity in both directions, in one direction, and then just say that each of the matrices describes one of the onion layers. Unfortunately, to have a nice theory, you should be able to communicate between neighboring layers. So for example, if you have 2x2 matrix describing a fuzzy sphere that is inside a different fuzzy sphere described by a 3x3 matrix, you want to be able to compare them somehow. For example, to take the derivative, you want to take this matrix, subtract from it this one, and then divide it by, for example, lambda. And it's impossible to take 3x3 matrix and do minus 2x2 matrix. So how can we compare those two matrices together? We need some kind of operation that takes matrix of size n times n, which we claim to be describing a fuzzy sphere, some function on fuzzy sphere, and then turn it into a larger matrix describing basically the same configuration. So you can see this is a configuration that is 0 here, non-zero on this, what is it, eastern patch of the fuzzy sphere, and we just want to make it basically larger and still describing the same field but on a larger fuzzy sphere. So how to do it? There is actually a super simple way of doing it. So the idea is, well, we can expand the smaller matrix into harmonics, expand the larger one into harmonics, but stop this expansion here. So it should be, it's a n+1, so it should stop at n, but we actually cut it off here. Or equivalently, we can basically take the coefficients from the smaller sphere and map them onto the larger one, and those that cannot be mapped, we just set to be 0. So the highest frequencies on the upper fuzzy sphere cannot communicate with their counterparts on the smallest fuzzy sphere because there is some kind of momentum cutoff. So this is a map that you can use both ways. Take a smaller matrix and define a larger one using the same coefficients and adding some zeros, or the other way around, taking the expansion, throwing away the largest momenta, and then mapping it on the smaller fuzzy sphere. This is the magical button that makes everything okay. It's back. So now we are ready to describe a version of a fuzzy onion theory. So as advertised, we can just glue together matrices of increasing size that describe the fuzzy sphere, so produce a new type of block diagonal matrix, but the size of blocks is increasing. So this is a 1x1 matrix, 2x2, 3x3, and so on. Now it's straightforward to define a potential this way. Just do the same thing we've done a million times in history of physics. Just square it and take the fourth power and make trace, now this very large trace of it. It's easy to do it, but we are not happy with this approach, so maybe some comments later on. Then you can take the angular part of the Laplace operator. Basically, each of the fuzzy spheres is filling the ordinary fuzzy sphere kinetic term, so nothing special going on here. But now, since we have the operator that allows us to go up and down, we can compare neighboring fuzzy sphere, so we can define the radial kinetic part of the Laplace operator as well. So basically, just take the second derivative, add some r's to make it the spherical expression of the radial part of the Laplace operator, and then we are ready to go. So we have a degree of freedom, or our physical field is this block diagonal matrix. This is the kinetic term, which is acting as ordinary fuzzy spheres on each of the blocks. And then we have this radial term that allows the fuzzy spheres to feel each other and interact in a way, plus some kind of obvious potential. What you can do with this, you can, for example, do Monte Carlo studies. And this was the motivation for me, as I was doing different studies of matrix models in Dublin. Before that, I was doing the fuzzy onion quantum mechanics in Bratislava. So I wanted to combine it somehow. So make a three-dimensional quantum space that I can use the same methods I have learned on fuzzy sphere models. So something that can be very, in a very straightforward way, simulated on a computer. So we have done some preliminary studies. Not sure if you can see this, but this is the theta angle and phi angle. So this is just the sphere deformed a little bit. This is the smallest one. Nothing actually can be going on there. It has just 1 degree of freedom. This is 2 by 2 and up to 10 by 10 matrix. You can see some kind of maybe, but it's maybe just seeing into things, but those patches aligning together on neighboring layers. So one of the things we can do, and we are actually working on, is doing Monte Carlo studies of scalar field theory on a likewise expressed fuzzy onion model. So our outlook, and already work in progress in some of those points, is to do a proper hybrid Monte Carlo study. It's slightly annoying. This is not a nice physical model because, for example, to do a Monte Carlo study, you have to keep changing between the matrices and still keep computing the expansion coefficients. So it's rather slow to simulate. It takes some time, but we are trying our best to have a nice phase diagram of this theory. Then we would like to define a nicer potential. And the reason is, as we have defined it so far, this way only each layer of the fuzzy onion communicate with itself. So fields on the fourth layer are communicating with each other, but not feeling the potential from the layers below them. So there is some non-locality on each of the fuzzy spheres that isn't propagated in the radial direction as well. We have some ideas how to improve it, but they are rather radical at the moment. Okay, then I would like to study some kind of a quantum mechanical model, at least to be able to compare our results with the exact results from the Fock space formulation of the fuzzy onion space. Uri is trying very hard to understand better the Fourier picture. How does the model look only in the momentum modes? How can you express the action and so on? But the final goal, at least, hopefully, will be to be able to make some kind of predictions, to understand something. So, for example, if you have three-dimensional quantum space, you can maybe model what happens to the singularity with inside a black hole. Maybe you will see some kind of oscillation. I don't know, but this would allow us to make some predictions about our real three-dimensional space. Thank you for your attention.
Questions? Please.
To the quantum mechanical model, there is the spinning top, right, in quantum mechanics, where you study, there's the homogeneous one, there's the inhomogeneous one. So you could study that model. Again, going back to this free Hamiltonian, you can just define it as xi square, and then these things are very nicely studied in quantum mechanics, and then you could compare them. Maybe just an idea.
Thank you.
Other questions? I just have one comment that I don't think you should be too worried about the potential being disconnected in a lattice simulation or in a lattice model, such as the Ising model. The potential at each lattice site knows nothing about neighboring potentials. Yeah, all of the communication is through the hopping parameters, and you've introduced the hopping parameter between the layers. So I don't think you should worry about that.
I'm not worrying that much about it, but that's part of the model, by the way, I slightly dislike, because the quantumness on the fuzzy sphere side is different than the discreteness in the radial direction. So there's.
But I mean, you're trying to do a radial quantization, I would have said, of the system, yeah, in a natural way. Yeah. If there are no other questions, people are anxious to go to lunch.
Yeah.
So let's thank the speaker again, and thank all the speakers from the morning.
Actually, I want to ask one thing about the computer living. Can you hear me? This is Masanori speaking. So I'm the next speaker, and I wonder what time I should log in and prepare. I cannot hear, actually. I will email you and ask.